All right, let's talk about this. So real quick, remind me, let's just zip through these. In terms of the numbers A and B and C if necessary, what's the commutative property of addition? A plus B, B plus A. Good, because to commute means to exchange, right? Multiplication example. Good, A times B equals B times A. How about associative? Okay, right, so I'll do that, let's see. Right? Associative, to associate means to group. So whenever we're doing an operation, like a binary operation, like adding or multiplying, we have to do pairs. We can group the operations in any order we want to. Right? So we could add A plus B first and then add C, or we could add B plus C first and add that to A, right? Okay. For multiplication, same thing, right? The quantity A times B times C equals A times the quantity B times C. Okay? Okay, identity properties. Now remember, identity is who you are. In terms of a number or a mathematical object, it's value, right? So this seeks to answer the question, what could I, add something. What could I add to something and not change it? Good. So 0 is our identity number for addition. What about for multiplication? And so 1 is what we would multiply something by and preserve the identity. So that's the identity number for multiplication. These two go together, right? So the inverse property, that's the one that says, what can I add so that I get back what for an answer? No? 0, good. So we want to know, what could I add to something so I get back the identity number for addition? So it would be, good, so it would be negative A. What do we call that again? Opposite, yeah. So the additive inverse for anything is its opposite. Okay. For multiplication then, we'd want to know what could we multiply something by and get back its special identity number, which for multiplication is 1. So what's that going to be? Say it again. A times 1 over A, good, which is really just a fancy way of saying what word? Reciprocal. Yeah, so the multiplicative inverse is just a reciprocal of something. Okay? And then finally, the distributive property, that one we all get, right? It's just, when faced with something like that in algebra, we just distribute, right? So we distribute the A to both parts. That's that. Okay. So name some properties then. Tell me which property is illustrated, for example, in 13.
Commutative multiplication.
Okay, so that's commutative property of multiplication. Okay. Okay. How about 14? How about 19? It's also distributive. Yeah, you can go both directions with that, right? $17? Yes, sir.
Number 13, is that commutative instead?
Oh, I'm sorry. Yeah, why did I say commutative? It's associative, isn't it? Yeah. Associative, yep. You're right. Thank you. Good. What about 17? Associative property of addition this stuff, right? Good. Well, that's probably good for them. Let's skip down to these guys. What about, so this time, for each of those numbers, each of those real numbers, we want to know what's the additive and multiplicative inverse. Okay? So what's the additive inverse for negative 8? 8. Yep. What's the multiplicative inverse? Everybody agree? Negative 1/8, not positive, right? Because these have to multiply to 1, and so you need a negative times a negative to get a positive, right? So an inverse always is the same sign as the original, okay? How about, what's the multiplicative inverse of 2/3? Okay. What's the additive inverse of the square root of 10? No. Not the square root of negative 10, it's close. We want to make a slightly different answer? Say it again? Negative square root of 10. Right, we're just going to multiply the original by -1. So really all you do is just put a negative out. If it started off negative, a negative times a negative is positive, right? So it'd be negative radical 10. What about the multiplicative identity? If a is the square root of 10, what's it going to be?
Would it be the square root of negative, or not negative, just one?
1, okay, but we don't have to put the 1 inside the radical. Just think of the whole square root of 10 as being a, right? So if the whole square root of 10 is a, then look what the multiplicative inverse is, right? It's 1 over a. So 1 over the square root of 10 is fine, right? Except, that's the correct answer. If I put that into a calculator, so let's see, if you got a graphing calculator, if you have a TI-84 of any kind, there's a little template for a fraction. It's kind of cool. If you hit alpha F1 and then enter, it makes a little fraction template. So 1 divided by the square root of 10 is that decimal, right? We'll come back to that. Oops. Okay, but do you remember probably Algebra 1, I'm guessing, probably not so much last year, but in Algebra 1, do you ever remember talking about in math that we don't like to have a radical in the denominator? Okay, we can't have a radical in the denominator, so we have to fix that. Now, let's think about that process for a second. So if we start off with 1 divided by the square root of 10, and I need to get rid of the radical on the bottom, what could I do? Just focus on the bottom. Remember that when you
Please
multiply...
excuse the interruption. If any students have not had their picture taken, teachers, please let them go down to the auditorium at this time. Thank you. This is the last call. Thank you.
Okay, so now think about multiplying fractions. Multiplying fractions, way easier than adding fractions, right? Multiplying fractions, what do? Straight across, right? You multiply straight across. So let's not even focus on the numerator part for now, because it's the denominators where we have the issue of a radical being stuck there, right? So what could I multiply the square root of 10 by to get rid of the radical? What would be the most convenient thing to multiply by on the bottom? Square root of 10, absolutely. So if I multiply the bottom through by the square root of 10, what's my answer end up being? 10, good. Okay, how come? Somebody explain that to me. What's one way that we could prove to ourselves that the answer is 10 when we do that? Yes, ma'am. Okay, so one way to think about it would be, we could say the square root of 10 times the square root of 10 equals the square root of 10 times 10, which is the square root of 100. And what's that? 10. Okay, good. There's another way that might even be easier. It's another way. The square root of 10 times the square root of 10. If we multiply 2 times 2 What's another way of saying 2 times 2? 2 squared. What's another way of saying 10 times 10? So what's another way of saying the square root of 10 times the square root of 10? Ah, okay, the square root of 10 squared. If we multiply something by itself, isn't that really the definition of squaring something, right? So we could write this as the square root of 10 squared, and what happens? Well, a square root and a square cancel each other, right? And so I end up getting a 10. Either way you slice it, we get 10, don't we? Okay. But now, so that worked great for the bottom, but think what's going to happen on the top. We're not wanting to change the decimal value of our answer, are we? Right, we're just trying to change the form of it. Another example of that would be, let's say you did some math and I said I wanted simplified answers. You're going to enter a group on some computer site. What if you get the answer 6/8? Is that simplified? What would you simplify it to? 3/4. If I type 6 divided by 8 into a calculator, what am I going to get? 0.75. What if I type in 3/4? 0.75. You see my point here? The value doesn't change. It's just the form of the answer. Same thing here, right? You want the answer to be the same. So what would I have to? What does that mean? What's gonna fill in the numerator of that fraction? If I want my answer to have the same decimal value as what I started with, which is just 1 divided by the square root of 10, it's gonna have to be radical 10, isn't it? How come? Well, here's why. Right there. Whoops, not right there, wrong one. Right there. Right? Because the way that we don't change the identity of something is when we multiply it by 1. So if I don't want to change the identity of what I'm starting with, which is 1 over the square root of 10, I better be multiplying it by 1. If I have the square root of 10 on the bottom, what do I have to have on the top if this fraction is going to equal 1? Square root of 10, exactly, right? So really, this is just a specific way of saying what we said very generally up there, a times 1 equals a, right? But for us, when we multiply straight across, 1 times the square root of 10 is just the square root of 10. And so there's our answer with a rationalized denominator, with no radical on the bottom. Let's just test it and make sure it works. So the square root of 10 divided by 10, what am I going to get? Better get the same decimal, and I do, right? So we just changed the form. Okay? Questions? All right, so last issue, and just a tiny one. Closure. This isn't that big a deal. It's not like you even see this in a lot of algebra textbooks, but it's something I want you guys to just be aware of. It's kind of an interesting concept. So the closure property. The closure property is a little different. The closure property only applies or makes sense when you're talking about some set and you're going to do an operation on that set. So for example, we're going to start off here with a set of integers and we're going to do the operation multiplication, right? Closure says that a set is closed under an operation or for an operation if the operation always produces an answer that's a part of the original set. Okay, so here's the question we have to ask ourselves then if we want to ask, is the set of integers closed under multiplication? Well, if I take 2 integers and I multiply them, do I have to get back a result that's an integer? If the answer is yes, then yeah, it's closed. If it's not, yes. If there's even just one counterexample where that's not true, then it's not closed. Okay. So what's your feeling about that first one? Well, probably just go with your intuition on this. If you multiply 2 integers, are you always going to get back an integer? Well, you are, aren't you? You can maybe even visualize this. Think about it this way. If I multiply 3 times 4, what does that really mean? 3 times 4. 3 groups of 4. Or 4 groups of 3, however you want to slice it, right? So imagine, for example, if you've got 3 groups of 4, say we get 3 little bags, and each bag has 4 marbles, right? That makes sense? If I dump the marbles out, I get 12, right? Wouldn't you agree that there's no way that I could take an integer number of groups, an integer number of marbles in each group? No matter what, I'm never going to get a fraction of a marble, right? Couldn't get negative marbles that way if I multiply them. Does that make sense? Well, actually, I guess I could because we're talking integers, but I can't get any fractions. Agreed? So yeah, that one is closed. Does that make sense? I'm always going to get back an integer. So that's true. Okay, what about this one? Irrational numbers are closed under subtraction. So once again, closure means I'm going to take a set of numbers, the irrational numbers, and I'm going to do something to those numbers and ask myself, is the output going to be, does it have to be one of those types of numbers? Does it have to be in that set? So if I subtract 2 irrational numbers, do I have to get back an irrational number? Oh, somebody have a counterexample? What do you think?
I was thinking of I what's another irrational?
Like square root of 2?
Yeah, I don't know.
So pi minus the square root of 2, that would be irrational. So that seems to indicate that it's always true. But can someone come up with a counterexample?
Pi minus pi equals 0.
Oh, there you go.
Rational.
Pi minus pi, how about? Right? So this one, we could come up with a counterexample. It's false because pi minus pi equals 0, and 0 is not irrational, right? Okay, so that's not closed. What about number 27? Whole numbers are closed under division. Right? Can somebody offer up an example? Come over here. Okay. Can you get an example? Can you think of how we can divide whole numbers and get back an answer that's not a whole number?
Like 6 by, or 7 by 6.
7 by 6, sure. 7 divided by 6 is not a whole number, right? That's a fraction. It can't be reduced. Okay, agreed? What about odd numbers are closed under addition? So I start with the set of all odd numbers, and if I subtract them, or add them, add 2 of those, what do you think?
This way, it's not close because you couldn't go.
There you go, it's false. In fact, I think it's always false.
2 odd numbers are subtraction.
Right, so we get an even. Okay, good. Questions on that? Okay. All right, so let's close things out. That's it for the math for the week. I'll collect the purple sheets on Tuesday.